turbulence modeling track. My name is Eugene de Villiers, and I'll be the host for this session. Our first speaker is Mr. Sina Samarbakhash from University of Rostock, and he'll be presenting a study of unsteady loading and turbulence in the wake of a ship with and without energy-saving device using a hybrid RANS LAS modeling. Please go ahead.
Do you see my screen?
Yes, it's there.
Okay. Hello, everyone. My name is Sina Samarbakhash. I am a PhD student at the University of Rostock. The title of my presentation is the study of unsteady loading and turbulence in the wake of ship with and without energy-saving device using hybrid RANS LAS model. Actually, the focus of this research is on a hybrid RANS LAS turbulence model. Professor Nikolai Kornev is the supervisor of this work. I start my presentation with the motivation, then I explain a little bit about the hybrid URANS LAS model, which we developed in our group LEMOS. That's why we call it LEMOS hybrid URANS LAS method. Then I show you a ship flow test case, which I apply this hybrid URANS LAS turbulence method for a CFD simulation of this ship flow test case. Then we go to the result and discussion, and at the end we have summary and conclusion. So in this slide, we want to talk a little bit about the motivation of this work, why we need to develop hybrid URANS LAS method. As you know, RANS can calculate resistance and mean velocity precisely, but it is not able to capture the unsteady effect, especially in the wake of ship hull, in the ship hydrodynamics application. So the application of vortex resolving method like LAS is necessary, but at very high Reynolds number due to high computational cost, application of LAS is almost impossible. That's why we go in the direction of hybrid URANS LAS method. In hybrid RANS LAS method, the boundary layer region is treated using URANS, and the flow far from the wall is calculated using LAS. If you look at the picture at the bottom of this slide, you can see very thin region close to the wall of the ship. This is the stern region of the ship. In this red region, we use RANS to solve a flow field, and the blue region are our LAS region. I mean, far from the ship surface, we have LAS, but at the boundary layer on the ship surface, we have RANS region. In this slide, we want to discuss a little bit about the theory behind a hybrid RANS LAS method, which we developed in our group in LEMOS. If you look at the equation 1, this is a general form of URANS and LAS momentum equation in general form. If you look at this, the stress term, which is in the blue color, TIJH, this is our hybrid turbulence stress term. When we are in the LAS region, this stress term would be our subgrid scalar stress from our LAS simulation. And when we are in the RANS region, this is our Reynolds stresses. I mean, during the simulation, it switched to RANS or LAS. But according to equation 6, we don't directly work with the stresses. Actually, we relate the stresses to the kinematic viscosity, nu h, and this hybrid kinematic viscosity will change between RANS kinematic viscosity and our subgrid scale viscosity. So how we can decompose our computational domain to RANS and LAS? If you look at the equation 7, we need to calculate the ratio of integral length scale to the cell size. If our integral length scale is bigger than cell size, then we are in the LAS region and we use nu SGS instead of nu h. And when the length scale is smaller than cell size, we are in our RANS region, and nu h switch to turbulent kinematic viscosity from our RANS simulation. So equation 11 shows that this hybrid viscosity is a weighted sum of our kinematic turbulent viscosity and subgrid scale viscosity with a blending function f. F is 0 when we are in a LAS region, F is 1 when we are in a RANS region, and in the buffer region between RANS and LAS, we use the gamma function for a smooth transition from RANS to LAS. So again, the hybrid Urans LES model, which we developed in Lemos, we call it in the short form LH, or Lemos hybrid model. And also there is a shielding version of Lemos, which is we call it in a short form SLH. This shielding function is introduced to overcome the artificial grid-induced separation, like the shielding function which we have in DDS. Now I want to we want to see the performance of Lemos hybrid model for the prediction of the wake and integral forces of the ship. Here you can see some geometrical information of the ship hull. The length of the ship at model scale is 6 meters. The block coefficient is 0.79 and the fluid number is 0.169. I use OpenFOAM for the calculation of Urans and also hybrid model. And also I use the CF mesh for generating a 3D mesh for this ship flow test case. In the table at the bottom of the slide, you can see some information about our numerical domain. The total grid cell is 33 million grid cells. The Y plus value is around 14. Or you can also see the size of our computational domain. Here, I want to directly go to the result. Here, you can see the time average streamwise velocity at the PIV measurement plane. If you look at the top right picture, you see the stern area of the ship, and there are 4 different cross sections. If you look at the red line, this is a PIV measurement plane. Actually, we are going to measure the velocity field at this plane. It is not measured yet. In the next month it will be done, but the simulation we already did at this PIV measurement plane after it is located after the energy saving device. If you look at the first picture, it is the result of Lemos hybrid turbulence model without energy saving device. As you can see, the unsteady in the flow field and this anchor shape, very common anchor shape. The second picture shows the Lemos hybrid turbulence model with energy saving device. As you can see, the flow field change a little bit. But figure 3, if you compare figure 3 and figure 2, they are both with energy saving device, but with 2 different turbulence models. Actually, the focus of this research is also on the different hybrid turbulence model. As you can see, the SST IDDS, it cannot, in this picture, it cannot reproduce the unsteady effect in the wake of the ship, and the result is very similar to the pure RANS result. As I wrote also here, the SST DDS and also IDDS, they failed to predict the unsteadiness of the ship wake region because of very large gray area. In the picture at the bottom, you can also see the difference in the flow field with and without the ST. In the following slide, I'll also show a very close view of the influence of different turbulence models. In this picture, you see the turbulent kinetic energy at the PIV measurement plane. Again, if you look at the top right picture, you can see the PIV measurement plane location. In figure 1, we have the turbulent kinetic energy with Lemos hybrid model without energy saving device. Then when we use energy saving device, you can see the change in the turbulent kinetic energy. It is a little larger than figure 1. But when we use SST DDS with energy saving device, I mean, if you compare figure 3 and figure 2, you can see that SST DDS, it cannot reproduce the velocity fluctuation. That's why we have a very small turbulent kinetic energy field, because it is mostly work in the RANS branch, and it smooths all this velocity fluctuation. I also wrote here that the transition from RANS to LES in DDS and IDDS has not been achieved correctly. That's why we have very smooth region for turbulent kinetic energy. The ISO line at the bottom of this slide shows the difference between the difference of the turbulent TKE field with and without ESD. Here I want to compare streamwise velocity and also TKE with 2 different turbulence models. This result is calculated for the location S2. Now, if you look at again to the top right picture, you can see the location S2. When we use SLH and IDDS, SLH, as I already mentioned, it is a short form of shielding Lemos hybrid turbulence model. When we use SLH, you can see the unsteady and this anchor effect of the velocity field. And also, if you look at the bottom picture for the turbulent kinetic energy field, with SLH, we can preserve the velocity fluctuation. That's why we have higher resolved kinetic energy field compared to IDDS. And the reason of this failure for IDDS is that the transition from RANS to LES in DDS and IDDS has not been achieved correctly, because it is they mostly need a very big flow separation to trigger transition from RANS to LES. But indeed, this ship is a very well streamlined ship, and that's why we have a very large gray area for our IDDS. This picture also shows the vertical structure visualized by Q criterion. The first picture shows the Lemos hybrid model. You can see the small structure in the wake of the ship. The SST IDDS, you don't see any structure. It is mostly working the RANS. It is very large gray area, mostly RANS branch of the SST IDDS, and it smooths all these small structures. If we come to the prediction of the forces, so far I showed the turbulent kinetic energy and velocity field. Now we want to see the performance of our turbulence model in the forces. If you look at the second table, it is the unsteady result. For the forces, we have also the measurement. We already did the measurement. Actually, our partner, they did the measurement. You can see that the SST IDS in the last column, SST IDS, the prediction for the forces is very good compared to the measurement, but our hybrid model, it has 40% error compared to the measurement. Actually, if you look at the first picture, K omega SST can predict the forces very well, and SST IDS also shows a very good agreement with the measurement. That's because SST IDS in this simulation work mostly in the RANS branch. That's why the result of the force prediction is very good. But now we want to work in the direction of improving our hybrid model for the prediction of the forces. That's why when I plot the distribution of spin friction coefficient along the ship hull, I see that the result of our turbulence model is below the RANS and SST IDDS. So we decided that now we are working on this new idea. We decided to decompose the computational domain like in the right, if you look at the right picture, in the way that we have 70% or 80% of our computational domain, we are using RANS, then we get a very good force prediction, and only use LES in the stern area. In this way, we also need the inflow generator at the interface between RANS and LES. Actually, we're working now on this idea. The result is not ready. Just I want to say how we want to improve the force prediction also. And the summary of my presentation, SST IDDS can predict force in good agreement with the measurement, while delay in RANS-LES transition results in smoothing of the unsteady effect of the wake. This ship is well streamlined and a strong separation are absent. So maybe the application of turbulent generator is needed for SST IDDS. Lemos hybrid model can predict the unsteady effect very good, but the prediction of forces is underestimated compared to SST IDDS and also RANS result and also measurement result. To solve this issue, we are working in the direction of decomposition of computational domain into the RANS and LES. The LES branch is only activated in the RANS area. In this approach, we need also inflow generator at the interface between RANS and LES to produce the resolved turbulent content in order to remedy the gray area problem. Yeah, we are now working the last items, and thank you for your attention.
Okay, we've got very little time. I'm just going to have one question. Apologies to the second questioner. Please talk to Sina directly after. So the first question was, aren't the turbulence models calibrated for aerodynamic problems instead of hydrodynamics? And then were the DS models used constants tuned for measuring hydrodynamic loads on the boat's plane, or are the deviations not important?
No. We didn't tune it for these special cases. Actually, we use K omega SST for our RANS region, and we use dynamic responsibility for our LES region.
Okay. Thank you so much, Sina. Unfortunately, we're out of time, so we have to jump to the next presentation. So any other questions, please ask them in the forum on the right-hand side of the interface, and I'm sure Sina, will you be able to answer there via text? Thank you very much.
Thank you.
Okay, our next presentation is by Naina Pisharotti. And Naina is doing her PhD at the Virginia Polytechnic Institute. Her talk is on transition modeling. Naina, please go ahead.
Sure, thank you. Yes, you're able to see my screen, right?
Yep, it's working properly.
All right. So hello, everyone. I am Naina, second year PhD student at Virginia Tech, and the topic of my paper is prediction of cross-flow transition using gamma transition model coupled with the Reynolds stress transport turbulence model. So to state my objective theory, the goal is to account for cross-flow induced transition and separation in the in-house built SSG LRR omega gamma transition model and validate it using the prolate spheroid. Now, before I go into what the SSG-LRR model is or how I account for cross-flow induced transition, let me give you a brief theory on the types of flow transition that are observed. One of the broader categories is the stream-wise transition, and this is a largely two-dimensional phenomena which encompasses modes like natural, bypass, and separation-induced transition. The second subcategory, which is the topic of the paper, is the cross-flow transition, which is a largely three-dimensional phenomena and is observed when cross-flow instabilities occur and disturb the boundary layer in the stream-wise as well as the span-wise directions. Now, these transition phenomena are popularly modeled by the transition models listed in this slide. Out of these, the most popularly used model is the gamma RE theta transition model, which is coupled with the K omega SST fully turbulent model. This was introduced by Langtry and Mentor, and then further simplified to just include the gamma transition equation, and was introduced by Mentor himself. This was also coupled with the K omega SST fully turbulent model. Recently, there was another transition model introduced by Ni et al. And this model uses the gamma RE theta transition model, instead couples it with the Reynolds stress model, the SSG LRR omega fully turbulent model. Now, all these models were initially introduced for stream-wise transition and later modified to incorporate cross-flow terms and their corresponding papers that discuss the inclusion and the incorporation of cross-flow transition in these models are being listed here. Now, coming to the model used in the current analysis, which is the SSG LRR omega gamma transition model, was developed by me and my colleagues initially for the stream-wise transition. So the formulation for this goes such that the SSG model and the LRR models, which are Reynolds stress transport models, are coupled the same way as the K omega SST models are. And the system is closed using the length scale determining equation omega to give the final fully turbulent SSG LRR omega model. Now, this fully turbulent model is then coupled with the one equation gamma transition model, which was introduced by Mentor that I mentioned in the previous slide. This altogether gives the SSG LRR omega gamma model. The advantages of this model is that first and foremost, it uses a Reynolds stress transport model for its fully turbulent formulation. And this helps in overcoming the drawbacks of Boussinesq approximation, and in turn helps in approximating complex flow fields better, since this model ends up calculating all the components of the Reynolds stress tensor. The second advantage is that the gamma transition model is a much more simplified version of the gamma RE theta model, as mentioned in the previous slide. And additionally, the gamma transition formulation uses only local variables and coordinate independent variables and correlations, and therefore makes the whole framework Galilean invariant. The third advantage of this model is that it has proven to predict natural, bypass, and separation-induced transition, which are all stream-wise transition mechanisms with equal or higher accuracy and compared to other state-of-the-art transition models. And this study has been submitted to the AIAA journal and is currently under review. But After all this, the most important limitation of the SHD-LRR model is that it does not account for cross-flow transition so far. So this is due to the fact that generally the transition criteria set for stream-wise transition model dictates that when the ratio of turbulent to viscous stresses reach a limiting value, the transition is initiated. And this transition criteria ends up being a function of stream-wise velocity gradient. And this correlation has been famously given by Abu Ghanam and Shaw. Now, this ends up preventing the model in predicting three-dimensional effects. Now, to overcome this, the simple solution is just to incorporate even the the span-wise velocity gradient into the transition criteria, as shown here. It is to be noted that unlike the stream-wise case, there is no definite constant that defines the transition criteria, and instead is a function of the Hartree parameter, which in turn is a function of the geometry and pressure gradient of the body. Pressure gradient along the body. So now that we know why we need cross-flow transition, let's look at how the transition model is formulated. The cross-flow and the stream-wise transition model frameworks for the SHD-LRR omega gamma model are pretty much the same. It's just, it follows the, includes the Reynolds stress transport equation, the specific dissipation rate transport equation, and the intermittency transport equation. The first two equations are adopted from Icefield et al.'s work. The only difference lies in the gamma equation, gamma transport equation, and specifically in the production of the gamma equation. So the production is given as the sum of the streamwise and the cross-flow components. And what you can see is that the streamwise transition criteria depends on vorticity Reynolds number, which in itself is a function of streamwise velocity gradient, while the cross-flow correlation is a function of the helicity Reynolds number. Now, one point that needs to be noted that the helicity Reynolds number is, the helicity itself is modeled as a function of velocity. And making it dependent on the velocity vector ends up removing the advantage of the model being Galilean invariant. And this is a prevalent disadvantage in all cross-flow transition formulations that have been made so far. These are the correlations that are followed and adopted from Ni et al. And Grave and Ni and Crumbian's work. And further details of this formulation can be discussed if you like later. Coming to the validation study of this formulation, the model was implemented on OpenFOAM, the most recent, well, not the most recent, but the 2006 version, and the DLR 6:1 prolate spheroid was chosen for the validation study. The grid used for this study has about a mesh resolution of 8.5 million cells, and it was ensured that the Y+ of the body remains, of the grid remains less than 1 close to the wall, so that the transition criteria can be carefully captured. And the mesh domain has been shown here along with the prism layer resolution magnified, and the meshing was done using snappy hex mesh. The operating conditions have been given here, where Reynolds number was 6.5 million. The turbulence free-stream turbulence intensity was set to about 0.2%, and the model was tested at 3 different angles of attack, 5, 10, and 20. The boundary conditions were set such that the spheroid had the no slip wall condition. The upper and lower walls of the spheroid were slip walls. The cross section of this domain was set according to the DFVLR experimental setup at the low speed wind tunnel setup, which is 3x3. And the inlet was given the velocity inlet, and outlet was given a pressure outlet condition. So going to the first case, which is the I'm starting in the descending order. So going to the alpha equal to 20 degrees case, you can see that the experiment and the cross-flow model fairly agree, at least in terms of the transition line. It's just that the transition point predicted by the cross-flow model is slightly upstream compared to the experiment. And can be seen that the fully turbulent model and the streamwise formulation of the model do not capture the cross-flow transition in any way. The three plots shown here are the force components observed in the three different directions. This is by no means supported by experimental data. It is just to highlight the fact that, you know, the forces predicted by the different models can vary largely, and therefore cross-flow transition probably will have to be taken into account if you want the right approximation of different components of forces. The next case is the alpha equal to 10 degrees Celsius. Sorry, not Celsius, sorry, 10 degrees. And the cross-flow model again seems to predict the transition pretty well. The transition line is slightly skewed, but apart from that, the transition point is fairly okay. It's just that it's slightly upstream compared to the experimental data, but otherwise the cross-flow transition is captured, as opposed to the other two models, the fully turbulent and streamwise models, where it is completely non-existent. And you can see the same trends observed in the three force components here, where the cross-flow transition ends up capturing the span-wise force a little, predicting a larger span-wise force component compared to the other two models. Finally, coming to the lowest angle of attack. And this is the case which is actually a little problematic, because this ends up, according to literature, it was said that this case shows both natural as well as cross-flow transition. And this ends up complicating matters, which ends up giving, you know, a complicated contour, as you see here. The cross-flow is sort of captured, but again, it's a little upstream, as well as the fact that the windward side transition is not really captured in this case. And as in the other cases, the streamwise transition model is able to capture some of the transition here, but apart from that, it's fairly poor. It's a fairly poor approximation. So these were the cases that were analyzed. Now coming to the summary. The SSG LRR omega gamma model is a desirable transition model because of the fact that it uses the Reynolds stress model based fully turbulent model and a simplified transition equation. The formulation to account for cross-flow induced separation and transition in the SSG LRR omega gamma model framework was implemented. However, the drawback was that it is not Galilean invariant anymore. The preliminary results for the validation study were presented. And when compared with the fully turbulent and streamwise transition model, the cross-flow transition model was able to predict the cross-flow transition much better. The prediction accuracy seemed to improve at higher angles of attack, as I showed you there. The angle of attack 5 degrees seemed to have poor performance compared to the other two cases. The transition location is being, as I mentioned, slightly predicted upstream of the actual location, and this has to be further investigated. And additionally, a point that, you know, experimentalists could also work on is that the forces were predicted by very differently by each of the models, and having experimental data to validate the plots shown there would be greatly helpful. And further research into modeling and predicting these forces needs to be carried out. Thank you. Any questions?
Thank you so much, Naina. There's a couple of questions. There's one from Joel Guerrero, but I think this one is for the previous speaker. Unless Joel says otherwise, I'm going to just wait on that. Then I have a question. Have you, I mean, this is obviously a very difficult problem. Have you considered the elliptic blending Reynolds stress?
So these
models?
are all, so the formulation for this model is based on the local correlation model, which is, that is followed by the gamma RE theta and the one equation correlation based models. We have not looked into algebraic modeling yet.
Okay, so then there's a question from Joel Guerrero. He says, if you can give any guidelines on how to set the boundary conditions and initial conditions for the model, you know, and what about the meshing and the regions where you have the transition?
Right. Yes, so a grid analysis for the cross-flow model formulation is underway, but for the streamwise model, you can actually refer to, whenever the paper comes out, you will be able to refer to the grid sensitivity of this model, but I can give you a brief account of what the grid sensitivity analysis gave. Is that, as most turbulence models are, it was most sensitive to the wall normal direction, resolution, and the y plus value of the grid. And that was the most the model showed most sensitivity to that. And another point is that since the model formulation is completely local and locally based, that is basically the model quantities are completely based on the boundary layer quantities and not on the free stream quantities. So it shows lesser sensitivity to the free stream turbulence intensity as opposed to K omega SST models.
I'm going to ask just one more question. There's more questions, so please, if you don't mind, afterwards just go and just look through them and answer. So there's one from Lila Kolazar, and she just asked how stable is this model? You know, we've had in the past problems with LRR models in terms of stability. You know, does this model have any problems in complex geometry with poor initialization, or does the SSG formulation mostly address it?
Right. So in fact, that research is also underway. We were actually trying to, the reason for formulating this model was to finally apply it to rotors. And currently the analysis on rotors is going on. And so far it's showing promising results, but yeah, I don't have anything to back that claim, but yes, the research is underway for that as well.
Okay, so we've gone over a bit, so thank you so much, Naina. This is a very interesting talk. My pleasure. So our next presenter is Professor Mario Tome from Prometheus IPVC PT, which I believe is part of the Polytechnic Institute of Viana do Castelo in northern Portugal. Mario, have you?
Yes.
Are you there?
Hello.
Okay. Could you share your screen and please start your presentation? Mario's presentation is on impinging jets, so very fundamental stuff.
Okay. So hello, good afternoon to all. So I will present this work, numerical investigation of the turbulent flow field in confined impinging jets. This work was performed by me and my colleague, Professor Cavadas, that has performed mostly the experimental work and some critical analysis also. So this the geometry of this internal flow is presented here, and the main dimensions. This the modeling work was performed using two symmetry planes, which reduces the geometry modeled to 25%. The experimental work was done with a laser Doppler anemometer and also some measurements with a flow meter. We use water as the flow in the lab. Here we can see the general apparatus, and in this here the cell test section. So we have very long flow to guarantee a full developed flow field when the flow arrives at the test zone. So this was done with acrylic transparent material, and we analyzed different Reynolds numbers. In this case, we will present the turbulent scenario, the turbulent modeling work for this Reynolds number. Here, the next slides, I will show some of the results from the lab. In this case, the measurement of the flow field in different sections. Here we can see the vector field and also the path lines. For z equal 0.45 W. Here we have some comparisons for different Reynolds numbers, but the modeling work is for the turbulent, for the higher Reynolds number here written in yellow. Some comparisons also with the Spalding's law and some other measurements on the laboratory and some other measurements of the turbulence in this case. So the mean velocity and the fluctuating velocity. So the fluctuating velocity is lower in the middle section of the flow as expected. And here also the velocity, the vertical velocity in different lines of the field. Here we can see the velocity field at the vertical plane, vertical cut. On our right, we can see some features of the bubble, the recirculation of the flow, which is critical for us to study and to characterize this recirculation. So before I show that this angle is 12 degrees with the vertical 12 degrees, which is a slow angle, slow sloping angle. And we also measure the transverse vertical velocity at different elevation lines. So the previous slides, as I said, were measurements, and now I will speak about the modeling work which was performed with OpenFOAM and also with ANSYS, which results of ANSYS are not shown here, only OpenFOAM. So we simulate the mass flow in rate as 0.48 kilos per second in order to achieve the Reynolds number indicative. And we use pressure outlet symmetry conditions and mass flow inlet and smooth walls. So the geometry is shown here, some 3D and 2D images of the geometry, of the mesh of the geometry, and here and the next images I exaggerated the angle as I duplicated the X scale in relation to epsilon. So here it looks like as a 24 degree. So here we can see different cuts, different planes of the X velocity. We can see that the flow is, these planes are repeated, mostly repeated. So the plane closer to us is close to the wall, and the furthest one is in the middle. So it's the symmetry. The furthest one is the symmetry plane. So it's mostly equal, but we will see that there is a small 3D feature. That's something that we observed in the lab, and we wanted to see if the modeling work achieves that small 3D feature recirculation. I will show it later on. So here are the same cut planes, but for epsilon velocity, which is the vertical velocity. The same for z velocity, which is mostly 0, unless closer to us, where we can see more heterogeneity on this z velocity field. All these velocities are in meters per second. The turbulent kinetic energy, square meters per square second. It's also mostly equal in the different, so the flow is almost two-dimensional. The same for the turbulent viscosity. Here we can see some vectors of the velocity colored by the turbulent viscosity. And here we have a sketch, a manual sketch. So this is not path lines, but it intends to represent the three-dimensional complexity of the flow field closer to the lateral walls. I show it, the images on the epsilon plus. Here we have on epsilon minus, but it's the same thing. So here we can see some three-dimensional isosurfaces of z velocity in meters per second, which reveals that the flow is at more heterogeneous, closer to us, so, closer to the wall. And here we can see some path lines that show this three-dimensional feature. So in general, we can conclude that for flow field and for turbulence, the errors were small. They were better near the symmetry than near the lateral wall, but the errors were mostly lesser than 6% in the mean flow field and also on the turbulence. We observed also a good agreement between the two models, two tools used in this work. We also conclude that the modeling work reveals this feature of the three-dimensional flow field, but the flow field is mostly two-dimensional, and we obtained a good performance with the standard kappa epsilon model, comparing the experimental work and the modeling work, and that's it. Thank you.
Thank you so much, Mario. We're almost out of time. I'm not sure if the session will I think it will probably continue. I have a question. Did you do any detailed comparison of the velocity vectors? You know, where are the big discrepancies, or are there any big discrepancies between the CFD predictions and the experiments? Because you have quite detailed experimental data.
Yes, I don't have those figures here, but it's more complex, and the errors are more pronounced in the bubble region. So we intend to use other turbulence models to study better this zone, and we had some other criteria in this evaluation in this recirculation zone that I have not shown here, but this is the critical region. Yes.
Okay. Well, yeah, it would be interesting to know if there's any improvements. Because detailed experimental data sets of very simplified flows like this aren't generally available. So will this data set be published, or is this proprietary?
This is already an old work. It was the PhD thesis of my colleague, and it is available. Yes.
Okay, thank you. So thank you again. That concludes this session. We'll see you back here tomorrow. I think there might be something happening tonight. Thank you everybody for attending. Thank you for all the presenters and the organizers. See you again. See you around at the event. Have a good day.
Thank you.
Thank you.